So this was the last slide that we studied in previous lecture. And we said that cut mechanism is a procedural mechanism that is somehow affecting the search method when we search for solution of a particular problem by going through goals A, B, C, D, E, F. Then we have that goals have to be sequentially satisfied. First A, then B, then C. So this is end, this here is end. If we fail to satisfy, for example, this B, then we backtrack to A. So it is going to be A, B, C, B, C, B, A, and we'll create all combinations of A, B, C that create results before uh, finding one that works. So you backtrack if you fail, of course. And then if you succeed with A, B, and C, satisfying these three goals, then you come to cut. And cut is the goal that always succeeds. Therefore, you're going to go to satisfy C, and then after that, satisfy cut and come to D. And then satisfy E, satisfy F. If you can satisfy all of them, A, B, C, D, E, F, then you create the result. Then the user comes and say, hey, give me more results, enter semicolon. So by asking for more results, it is going to go back from F to E, from E to D, and will backtrack between this D, E, F to create more results. However, if this is not possible, it is going to try to backtrack from D to C. Well, this is going to be impossible because you cannot go in this direction from D to C. This is the fence that is not permitting you to go back. Therefore, you have A, B, C, and then you have cut and D, E, F. Okay, and therefore, when we have that, the cut is using the first combination that is satisfied with A, B, C, and then is backtracking through D, E, F. By this is commitment that we have, and we cannot go and find any other combination of A, B, C. And this is useful in variety of cases. And the cut is practically mechanism to restrict or to terminate the search process. So it is very important because it improves performance. It is simply removing unnecessary search operations. On the other hand, if you look at ABC, these all are goals that are described. This is not the procedure. However, cut is a procedural element. It is procedural element in one non-procedural world. And you are going to see it in many examples and use it. So it is not consistent with non-procedural approach to problem solving, but if you want to make efficient programs, it is necessary. So let me show you an example that is going to clearly illustrate what's going on. So the idea is this one. We want to compute factorial function. And how to compute factorial? Well, factorial, like all other recursive programs, has boundary condition. So the factorial of n is 1 if n is less than 2. So if you have that n is 1 or f n is 0, factorial is going to be 1. So factorial of n is 1 if n is less than 2. And if this is satisfied, you are going to get as the result 1. On the other hand, if n is not less than 2, then you're going to fail this first line and you're going to drop to the second line of code. So this here is the rule. And if this rule is not satisfied, we go to the other rule. So the point is that PROLOG is always going top down and left right through rules. So top down means after you fail that n is not less than 2, you drop down to factorial of n is f. And this is the rule that is satisfied if we have these strings that are satisfied in this sequence, first and second and third. You can write it in the single line going left to right, or you can write it one under the other, which is equivalent way of writing that. So we have that factorial of n is f if what? I can compute the new variable n1, which is n minus 1. So this is assignment. N is n minus 1. And I go and compute factorial of n1, which is f1. And I get this result. If I get this result, then compute this value f as product n times f1. So take this n, multiply by this f1, and you get factorial f, and return this f. So this is the way how we write program in PROLOG. So factorial of n is 1 if n is less than 2. If it is not less than 2, Pedro, what's the question?
I noticed you calculated n1 in the first line. Is it possible to put n minus 1 in the factorial function, or do you have to calculate it beforehand?
No. You have to provide here two objects. And this object is not n minus 1, but it is a new object. Otherwise, it is not constructed in a way that you have recursive functions in procedural languages. You have to create a new object, n1, and use this. You cannot put expression inside.
Okay,
you
thank
put
you.
a new object, yes. But again, it is going top down and left right. One thing that you see here, and also, thank you, Pedro, for raising your head, but if you just unmute your microphone and interrupt me by asking question, that is also perfectly okay. So thank you for raising head, but you don't need to do that. If you just start speaking, we hear you. So here is here is practically a loop, because what you are doing, if you have factorial of 5, for example, then it is going to create here 4 is 5 minus 1. And this is going to start asking, give me factorial of 4. And then this factorial starts the search again from the beginning. So this factorial jumps to first one and then second one. And if you have this one, it is looping through this. So first, second, first, second, first, second. So recursion is equivalent to iteration. It is repeating computation over and over again. And sooner or later, you are going to satisfy this condition. When you satisfy this condition, then you start returning from this factorial to this line here, and computing f is n times f1. So if this is partially understandable how this works, we have two possibilities. Either we write it in this way, or we write it in this way, but then put cut after the boundary condition. So to prevent to generate more solutions, because how many solutions we have for factorial? If I have factorial of 5, it is 1 times 2 times 3 times 4 times 5 equals 120. Okay, now, is there any other solution? No. Factorial of 5 is only 120, and if I ask, give me more solutions, there is nothing more that I can get. So it is reasonable to put here cut and prevent the search mechanism to continue. Because if you don't do that, then here is what happens. First of all, if I have factorial, this one and this one, I can make the listing of that. You see that here I call this N1 and F1, etc. However, listing in SWI PROLOG is always showing internal notation of the program. And so the variables are renamed to A, B, C, D, E, F. This is the name list of variables that are used in PROLOG internally. So it says that factorial of 1 is factorial of A is 1 if A is less than 2. And second rule, factorial of A is C if I can compute B, which is A plus minus 1. So it is adding minus 1. It is writing in this strange form, but that is what is going on. And factorial of B is D, and then this C result is A times D. Now, let us focus on what is going to happen in this case and what's going to happen in this case, which is completely equivalent, but it has here cut. So maybe we go here and first look at what happens in the case with cut. If I say, give me factorial of 0. So factorial of 0 is n. What is n? PROLOG is taking this factorial of 0, putting here 0, and finding that 0 is less than 2, and then returns to me 1. Returns this 1. And then after returning 1, the language processor is looking what is the next. So when it returns 1, practically it is matching factorial 0n with this A 1. So A is 0, and then is coming here to see is 0 less than 2. Yes, it is. However, it is not going to stop here. It is going to go over the cut. And then will come between cut and this dot. So it is going to be at the very end, and there is nothing more. So after giving this solution n equals 1, PROLOG see that it cannot go left, it cannot go right. And then it is simply giving me this prompt and say, what do you want now? So this is one and only solution that is generated, and ask me, what do you want now? Then I say, I want factorial of 5. Then it is putting here 5, going to find whether it can satisfy 5, 1. It cannot, because 5 is not less than 2, and it fails to satisfy first rule, drops down. Factorial of 5 is C. If B is 5 minus 1, B is 4. Tries to compute factorial of 4. Factorial of 4 is D. Can this be computed? In order to compute that, you can to start search from the top. You go to factorial at the top, and then try to see whether this is satisfied. This is 4. 4 is not less than 2. You fail with first one. Drop to second one. So you have here 4 and compute 3 and try to find factorial of 3. Factorial of 3 again brings you to fail first, succeed second. Then you go in this loop 5, 4, 3, 2, and then you come with 1. When you have 1, then you succeed. 1 is less than 2, and you return this 1 here. And then after that, you return and compute C is A times D, and it is returning multiple times and creating here 120. After this is done, when the last 1 is multiplied, we again have here cut, and therefore it is not going to continue, but it is going to give me this result and put again the prompt and ask, what do you want next? On the other hand, if I have this program here, which is identical to the right-hand side, but it has no cut, then if I ask what is n if I want factorial of 0, it is going to come here, we'll put here 0, and then 0 is less than 2, and it will return 1. It will say n is 1. And where is going to be the pointer? Here. It is going to be here after A is less than 2, pointer of the search engine. And then what happens now? I have the correct result, n is 1. And PROLOG will wait here, cursor will blink here, waiting for me to decide what I want to do next. What I can do, I can simply press return and say I'm satisfied with this. The same happens here when I have factorial of 5. Factorial of 5 is 120. And I'm supposed to press return to say I'm satisfied, I don't need anything more. But since this is the search mechanism that can continue, I can also put a semicolon. So this semicolon and this semicolon, all of them are input that I intentionally put inside. So I'm asking PROLOG, continue search from this position. To continue search from this position, you are practically going to this second line and computing after 0, computing -1, -2, -3, etc. But in this sequence, 5 times 4 times 3 times 2 times 1 times 0 times -1 times -2 times -3, you're going to have somewhere 0. And you are going to create this sequence of zeros. And it is going to go in this direction forever unless you press return. So you don't want to have this. And therefore, if you want to avoid to have this wrong continuation of the search process that is defined by recursive function, you should terminate that somehow by putting here cut. Now, how this works is not self-evident at the beginning. And you have to think very carefully what happens when you go through this mechanism, if you have or not have cut, and how this mechanism is working. It is going top down, left, right, always. So here, left, right, and then when you fail the first rule, go to second rule. So it is looping through this. However, it is easy to see that if you put here not is, but put pattern matching equality. So put here equality. This is not going to compute the result, but it is going to show you the anatomy of the work. So when I have here that f equals n times f1, these are numerical values. So you are going to get that this f is, for example, 5 times 4 times 3 times 2 times 1. And if I have this program that has no cut and this that has cut, you can see the anatomy of that work. So here is the program that is listed here. You are now making the listing of this factorial and get factorial, which has here not assignment, but pattern matching equality. So what you are going to get when you compute factorial of 5, you're going to get 5 times 4 times 3 times 2 times 1. It is not going to compute this, but it is going to return this factorial value c as this pattern, which shows exact multiplications. But when you say that n is a times d, that means match c with this pattern. And if this pattern is 2 times 1, then c is 2 times 1. And if you multiply this by 3, then it is 3 times 2 times 1. So you start with 5, and you have 5, and then times 4 times 3. This expression is matching two patterns. It is not computing the arithmetic value and assigning it to C. So therefore, you don't have that this is assignment. This is pattern matching. And this is convenient here to show you what happens. So you see what is happening. It is multiplying 5 times 4 times 3 times 2 times 1 times 0 times -1 times -2, etc. Always terminates with the boundary condition 1. But unfortunately, when this happens, you have here 0 in between. And this is the reason why you have here 120, 120, 0, 0, 0, 0 to infinity. If you have here cut mechanism, then the situation will be different and better. You are going to have that if I have cut mechanism, if I say factorial of 0 is what? It is going to match pattern 0, and n is going to be matched with 1. We'll say n is 1, and after that, we'll stop program. If you ask, tell me what is factorial of 5, it is going to tell you it is 5 times 4 times 3 times 2 times 1. which is not the result, but it is showing you the order of performing operations. So this, what we do here by putting pattern matching, is useful for learning, for seeing how the process of computation is done, in what way. So this is what you get as the result, but it is not performed arithmetically, because in order to have here arithmetic operation, you must have ease. You have to have assignment. So if you have assignment like this one here and this one here, so on the right-hand side, you have an operation that must be performed, operation with numbers. It must generate a number, and this number has to be assigned to F. That's what ease is making. If you put here equality, this is pattern matching equality, and F has to match this pattern. So if this pattern is 5 times 4, F is going to be 5 times 4, and then times 3, and then times 2, and whatever is happening in this loop is going to become visible, and you will get practically a result like this. So if you say, I want factorial of 0, nice. Factorial of 0 is going to be what? 1, and you have correct result, but you are not satisfied. You say continue search from here. And this is recursive program that can loop forever. So what happens here, you get that the next result is 0 times 1, because 1 is decremented to 0. And then 0 is decremented to -1, and -1 to -2. And it's saying 0 times -1 times -2 times -3 times 1. And of course, all this generates zeros. So this explains why you have these results that we had here, 1, 0, 0, 0, etc. But it also explains why cut can be useful to eliminate these things. So this program here is not wrong. So this program here is correct program and generates correct value. The only thing is that it does not terminate after correct value, and gives you the possibility either to continue search or to press return and say, I'm satisfied, give me possibility to give you another assignment. So this is what happens after we do this. Okay. So now, any question about this? This is not trivial and needs a little bit of effort to understand, but it is showing you the anatomy of execution of these rules, top down and left right. Okay, in this line here, you have first, second, third. So this is left right, which is again top down if you write it in this way, but it is in the Siegel rule, you have first to satisfy this, and to satisfy this, and to satisfy this. So you have first and second and third. One thing that we must understand immediately now, you can never come to this line unless you failed the previous one. So if you have rules, fact, 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 fact here, PROLOG search engine will start with the first factorial at the beginning. And if it fails this, we will come to the second line. You cannot come this line if this line if the previous line is satisfied. If it is satisfied, it is going to create the result and will give you result. And you will never come to this line. Okay. You come to second line when you fail previous. You come to third line when you fail first and second, etc., etc. So this is the way how PROLOG works. Now, when you have factorial of n is 1, if n is less than, what does that mean? That means that after that, you have to satisfy more conditions, and one of them is cut, and then the pointer is going to be here. Pointer is between cut and end. And of course, PROLOG search engine knows that it is in this dead end position. So after creating the result that is obtained from here, the Further continuation is impossible, and therefore, as soon as the result is delivered to the user, PROLOG terminates, because it knows that cannot go back over this cut, cannot go back to previous things, and has nothing after. So it is simply terminating the program. Return over cut is not possible, and program regularly terminates. That's what happens here. Now, few words about input and output. Input and output you can learn in 20 seconds. If you want to read an object, you say read object, X. And whatever you enter in your keyboard, it is going to be the value of X. If you have X that has some value, by saying write X, this is going to be displayed on the screen. So read is reading X from keyboard. X is displayed on the screen by writing X. So read and write. Read is extracting, and write is displaying. And then to make a little bit of better formatting, there is tab. Tab is insert and spaces. So if you have first name and family name, you put space in between, for example, so that you don't glue them together. If you want new line, you put NL. NL is reserved keyword for new line. Okay. So this looks trivial. Read X, write X, and tab N. Well, it is far from trivial. It is very easy to use, but inside is extremely complex. Let me tell you why. There is a concept that is called first-class language. First-class language has to satisfy a variety of conditions. There are 10 conditions that have to be satisfied. One of them is that all objects of the language must be readable and printable. Now I can ask you, is C++ first-class language? Of course, it is not. If you have that you want to read something, extract from input stream, or display something, insert in output stream, there are just a few things that you can read. You can read an integer, you can read a real, you can read the character, that's fine. You can read the string, that's also fine. What else? What else? Nothing. Nothing else. If you want to read something else, go home and write your program for overloading the extract and insert operator, and then you're going to have more. So if you have an object that is a triangle, it has A, B, C, it is triangle. Can you read triangle in C++? Of course you cannot. Can you display triangle? You cannot. Because extract and insert work only with numbers and with string and with characters, and that's it. So you can say, how about this X? Well, if the language is first class, then at least read and write can be capable to accept any kind of X, anything that is legitimate object of that language, which means when you read X, you have to have lexical analyzer, syntax analyzer, and semantic analyzer, and to check that all these three things are satisfied. And then you can give that to the user. This is a very complex operation. So let me show you an example. When I say read int, int is a variable name. You can put X here. And if I enter inside 123, so this is a prompt for entering. It is not vertical line, means it is not finished, and this column means tell me what you want to put inside. So I enter 123. The reply will be int is 123. So this is the result of this operation that is given here. So obviously, this object that has name int is instantiated with 123. Okay, so now I go here and say read real and enter point 123. When I do that, real will be 0.123, a real value. Then I come and enter list. List is 1, 2, 3, 4. So it has here a bracket, and then first object, second object, third object, fourth object, closed. It is going to convert that into list and tell me list is 1, 2, 3, 4. So now it is capable to read list of any size and any kind of content. I try with strings. I say read X, and X is this string. First, backslash n is new line, second, embedded in string, new line and second. And then this X is going to be echoed as first, second in 2 lines. If I say write X, this write is this X object is now this string, and therefore you will get X is, X is first, second is what is read here. And when I say write X, I get first, second, because it is writing that. And this is the first, and then comes X, which is first, new line second. But again, it understands that this is a string. Or if I say, read, this is a string, it is going to give me string equals, this is a string. Now, a list can be made of any kind of atoms. So I have here bourbon and soda and 4. So this is symbolic atom, this is numerical atom. And it gives me list, bourbon and soda 4. So this is what is converted by going through my input and understanding first that this is list, that this is 1 atom, second atom, third, 4, that they are separated by commas, and you get this as a list. So let us try with something that is more complex. Let us put list inside a list. So I have list that has 2 components, first list and second list. So in order to understand that this is first and second list, you have to have inside lexical analyzer. There is no doubt about that. You must start analyzing from this bracket to this bracket. Then you have to have syntax analyzer, because you cannot understand that this is the list if it is syntactically incorrect. Okay, so if I come here and say read L, and then PROLOG says, okay, give me your L. And I put here beginning of the list and put here 1, 2, which is first list. Okay, put the second list 1, 2, here is AB, here is 1, 2. And then there is no closing bracket. If I press return here, it is going to tell me, hey, you have an error. Stream user input in character 15, syntax error, operator expected. I want to see operator here, the end of this bracket. So this tells you that this read command has inside lexical and syntax analyzer. If you read this with stupid scanner that is available in C, C++, Java, and similar languages, scanner understands nothing. Scanner is scanning from left to right, giving me character after character, and will give me this string here and will tell enjoy. This here, I don't know what is this, but maybe you know what is this, and do with it whatever you want. Well, PROLOG is not doing that. PROLOG is having reading plus understanding what is inside. So after you enter this, before continuing, PROLOG has to check that this is lexically, syntactically, and semantically correct. And after that, gives me list is first list, second list. And of course, this is a correct result. But before you get that, there is a very detailed and complex analysis that is based on taking legitimate object of the language and transforming this object into internal notation. Therefore, going back to these simple commands, read and write, you can read everything that is legitimate object of the language, and you can display everything that is legitimate object of the language. And this is a big news, because regardless how simple it is, it gives a huge comfort to the user to read whatever you want and to display whatever you want without having to overload operators so that they display something that you want, an object that you want to create. So here, all objects are readable and printable. You're going to see the same mechanism in Scheme. Scheme is first-class language. PROLOG is not first-class language, but it has properties of first-class language. And all languages, including C or C++ or Java, etc., all of them have components of first-class language, but only a small number of them are first-class. And we are going to have one of them, which is either Scheme or Racket, that have these properties. So after this, we can use read and write in an application. Is there any question about this here? Okay. So let us use this, what we learned so far, cut and read and write, to write this program like Yozo Wine and like Eisman Wine. So now we want to do this. We want two different people are friends if they like the same thing. So stop search when the first pair is detected and generate a message. That's the assignment. So we say friends 5 are X and Y if X likes something. This something is W. And Y likes the same thing. And X and Y are two different people. And then don't permit more solutions than this one. So put cut here. And after that, display the message. So the message will be, for example, that X is Yozo, Y is Eisman. So I want to display this message. Write X, Yozo. Write and Y. So Yozo and Eisman are friends because they both like write W, whatever is W. So a new line after that, and then wait here to see what will the user like to get as the next thing. Okay, so the point is here after new line. All this is satisfied if X is Yozo, Y is Eisman, and W is wine. So the message that is going to be printed here from this program is Yozo and Eisman are friends because they both like wine. Okay, so this is the message in plain English that is generated by this program. What happens next? Well, what happens next is this. You tell program that you want to see what is X and Y. So you are not generating just friends, but you are asking, show me X and show me Y. So after that, after this message is displayed, PROLOG is saying X is Yozo, Y is Eisman. And then is waiting here to see what will happen. So it is not finished. You can continue this search. Then I come and say, give me more friends. Put this semicolon. You see this semicolon here. So I want to continue search. Where is the pointer? Pointer is here. What happens now? There is no other way where to go, and PROLOG is backtracking. It is going back over this new line. This is a passive element. Nothing happens. Going over new line, over right, over this right, over this right, over this right, over this right, and then is hitting this cut. When it hits this cut here, then it cannot continue to generate new combination of X and Y, and therefore it gives me no. This no is generated after backtracking to this cut, and you can put cut at the end if you want. The same mechanism will be. The new solutions are always generated by these likes and dislikes, not by this X is different from Y. You have to instantiate X, you have to instantiate Y, and then you can check whether this is true or false. Therefore, friends, friends 5 will create this useless result. So if you want to eliminate this, you can have the same program, but without XY here. And this is done here. Friends 6 don't have X and Y. They just say Yozo and Iceman are friends because they vote like wine. New line, and that's the end of the program. So this case, we eliminate double results. We have one result, and we have only this message here. Yozo and Iceman are friends because they both like wine, nothing else. Okay. You can also remove this. You can remove this cut. If you do that, like here, then you create all permutations. Yozo, Iceman, Iceman, Yozo, you are going to get two messages if you keep adding semicolons. What is, of course, not useful, but it is possible. And therefore, we have all permutations that are created here. You can also have the situation where you either say what they like together, or you don't say what they like together. So this is something that shows, of course, all results plus W. Then sample program number 9 is the case when we want to create a rule for big friends, that people are big friends if they have more than one thing in common. So they have two or more things that are similar and that are in common. Therefore, big friends are X and Y if X likes something, W, wine, and Y likes something, W, wine, the same thing. And X likes something, F, which is food, and Y likes food, for example. And then X and Y are two different people, and wine and food are two different objects. And then comes cut. So the rule that the big friends are people who have two things in common will generate, of course, the situation where W and F are the same thing, but you are going to fail here and backtrack. So the only that will come till the end is the situation where you have two different people who like two different things, because X and Y must be different and wine and food must be different. So it is going to have to satisfy first, second, third, fourth of these likes predicates, and will have to satisfy also this condition and this condition. And after that, will not be permitted to go back. If you have to compute all possible things that all permutations that you have, and to show all solutions, remove this cut. This cut is going to create only one solution and will not permit you to continue search. However, here, the pointer is going to be after this last condition. And if you enter semicolon and say, give me more, it is going to backtrack, 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 comes to this here and try, is there anything else that I can satisfy? If not, go back here, go back here, go back here, and combine all these things and give me all possible solutions. So what is going to be generated here? For example, that Yozo and Iceman are big friends because they like food and wine, and then you are going to have that Iceman and Yozo are big friends because they like food and wine. So it is going to be repeating and permuting the same conditions, what is not necessary. So you are usually going to have this cut here that is eliminating this problem. Okay, any question about this? Okay, so what are the trivial solutions that we have studied so far? First trivial solution is repetition of the same result. So you can say friends are two people because they like the same thing. But the first trivial result will be friends are Yozo and Yozo. And after that, friends are Iceman and Iceman. So you repeat the same result. How to eliminate a result that is saying X is same, Y is same? Well, this is eliminated using the condition that X must be different from Y. And in that case, this is not going to be acceptable. So this is, of course, going to be correct. X must be different from Y. However, this is not the only trivial solution. The other trivial solution is permutation of previous result. So permutation is when you have that you get X is A, Y is B, and then the next solution is X is B, Y is A. So you can say Yozo Iceman or Iceman Yozo. You don't want to get this permutation in many problems. And if you want to eliminate that, you have to use cut. And when you cut, you generate a single solution and then don't continue to create more solutions. Stop when you have cut. And this is two of trivial solutions, repetition of same result and permutation of previous result. Result that you already obtained, and now you want to make permutation. In PROLOG, you can overload operators same as in C or C++ or in Java. That means predicates are identified both by name and by the number of arguments that they have. So imagine that I want to compute maximum of two numbers. So I have number X and number Y. The maximum can be either Y or X. So the maximum of xy is y if x is less than or equal to y. So what we have here, we have less than or equal to. Pay attention to this syntax detail, that it is not written less than or equal to, but it is written equal to or less than. This arrow is always pointing to equality sign. If it is greater than or equal to, then this is turned upside down, left, right, and you have again less than and after then equal to. But if you have equal and less than, you write it in this way. So it is not the same as what you have in other languages when you have less, equal, and greater. Equal, you always have to write in this way. This is syntax. Then if this is not satisfied, then you go to second one and satisfy it with x, if x is greater than y. So this is maximum of two values. Now, we can call maximum of three values, x, y, z, the same way, the same name, max. But this program is different from this here because it has three variables. So this is a different program. So you can say maximum of three variables is obtained by computing maximum of two variables, x and y, and storing that in this temporary location t. And then when you have this t, find maximum of t and z, this temporary, and this z, which is the third variable. And this is going to be stored in max, and then return this max out. So first, compare these two, get the intermediate result t, and then t and z to get max, that is going to be the complete result. Okay, you can do it in that way. How to make a maximum of four variables, x, w, x, y, z? Well, max is going to be now using max of three variables. So you have max of x, w, x, y, and this is t. And then this temporary is compared with z, using this max here. Now, at this point, you can say, okay, this is trivial, but is it possible that you have one respectable language that doesn't have maximum function in the library? And the answer is yes. It has a library function max that has two variables. So if you say max of x, y, without this third variable, this is the function that is going to return the maximum value. So you can say by using library function max, you have that this maximum of 4 variable w, x, y, z is max. If you have that you compute temporary variable p, which is maximum of wx, and q, temporary variable, which is maximum of yz. So you see that here you have ease. You are assigning this value to p and this value to q. So this p is the winner of this semi-final matches between w and x and y and z. And then you get two finalists, p and q. And then you have the final match between P and Q, and this is generating the winner of the tournament, which is max, that is returned here. Okay? Or you can say M is max of x, y, max of y, z. You can write it in this way. These are based on library function. If you use this function here, this is not a library function. It has 3 arguments, and this is homemade maximum. All this works fine. So maximum of 1, 2 is M. M is 2. That's what PROLOG is answering. If you have max 4 of 1, 3, 2, minus 1, what is M? M is 3. So that is what PROLOG is returning after going through this situation that we have here. Okay.
Can you overwrite the library functions?
No, because this is not overwriting a library function. It has it has 3 variables, and library has 2. So you cannot define a library function M of x, y that is doing something else. You can write max of x, y, but if you do that, then you are ruining this max and making something that is not useful. It has no purpose. Or you have sine of x, and you say, I'm going to compute inside logarithm, not sine. That is not a good idea. But this is the legitimate way to do things, because this max has 2 variables and this one has 3. So these are two different things. Then there is a possibility during the normal execution of programs to add and delete clauses. So you can do that. And this is good for testing and debugging purposes. So there are 3 things that you can do. You can assert A or assert Z and retract. So let me explain how this works. First, you want in the middle of execution of program to add one more component to your running program. So you want to assert new fact. So you have people, male and female, and say assert male is Tom. So this male Tom is going to be inserted in the database of facts. And then you can say assert male Tom in 2 ways. You can say assert A or assert Z, or assert without A and Z. Now, in all PROLOG systems from day 1, this assert was available. Now, SWI PROLOG decided that this is redundant with assert Z, which is the same. Now, A is the first letter in alphabet, Z is the last letter in alphabet. So if you say assert A male Tom, you are going to add this fact as the first fact of male group. So you have mail Peter, mail Tom, mail John, mail whatever you want. And then when you are adding this mail Tom, it is going to be put either at the top or at the bottom of that mail group. So you are supposed to put all this male together and all female together, okay? But you can insert that male is Tom either at the top or at the bottom. If you put assert without anything, it is going to be in the bottom. So this version 8, I downloaded version 8 of SWIPO, and this version 8 claims that this is deprecated, in SWIPO. So soon they are not going to support this anymore, most likely. And this is something that happens with languages that are alive. They are over time having evolution, modifying things, and you get new properties. So if you work with assert A and assert Z, that is going to work perfectly okay. You can also remove a clause during execution. You can say retract mail Tom. So you erase this fact, mail is Tom, from the database of facts. Why would you do that? Well, for testing purposes, you want to see how this works. So here is an example that perfectly clearly shows what we do. So you start PROLOG and enter assert car is Ford. So you have car is Ford as a fact that you insert in your database of facts. After that, you say assert car is Honda. And then the second fact, car is Honda, is inserted in your database. What you can do now is to say, give me cars. So car is X. And so what is X? And you are going to get X equals 4. And then that's a correct answer. And you enter semicolon. PROLOG is going to wait at this position, waiting for you to enter something. And you either press return or semicolon say continue search more, give me more results. And then more results will be X is Honda. So first X is Ford, X is Honda. You say give me more results. PROLOG says no, there are no more. That's all what you have. Then you can continue and say retract car Ford. So you go to database of facts and remove this fact car Ford. And it says yes after that, okay? And then you say, give me car. And result will be car is Honda. And then when you ask, give me more cars, it says, no, you don't have more. You have only Honda in this database. So practically by retracting car Ford, you erase this fact from the database of facts. So you can say, for example, male is Tom, male is John, male is Peter. And after that, female is Anne, female is Mary, female is Kim, for example. And then you assert all these things. And you can say assert person is P if P is male or P is female. So now you have the new rule that you assert, insert inside. So insert, assert rule that says person is P in parentheses if colon hyphen, and then after that say it is either male or female. And then you can ask, give me person. And when you say give me person P, it is going to tell you P is first male, second male, third male, first female, second female, third female, and all of them will give you. So you can dynamically do these things. It is not very important because for serious problems, we don't do it that way. But for testing purposes, it is rather suitable. And for learning at the beginning how to put things in database and how to retract them, use assert or assert A and assert Z. Assert A will put Ford at the top of the car group, and assert Z will put car at the bottom of the car group. PROLOG will work if they are not continuous, like you have male, female, male, female. But it is like that, and in some cases it is creating warnings and complaining against putting mixing these various facts in an arbitrary order. That's not a good idea. So here is an example of using assert for more complex programs. So we have assert maximum of 4 variables is max, and you say this is going to be if maximum is max of A, B, and max of C, D. So I'm going to use library function max. Max of A, B will return a value. Max of C, D will return another value. And then max of these 2 values will return the third value that is stored in max, and max is returned from here. So we use library function, and we assert this by putting this program directly in the running program as one additional clause that you have. And then if you say, give me max 4 of 4, 3, 2, 1, you get 4, of course. And here you get M is 4. And you can also assert that max 4 of A, B, C, D is max if max is max of max, etc. So you have A, D, C, B. This is a different order of doing things. So this was A, B, and C, D. Now you take A, C, and B, D. You take each second one. And the result is the same. Of course, if you compute 1, 4, 3, 2, you get 4. And here also you get 4. So this is how you can insert temporarily this rule max 4 in the database of rules. And of course, you have also possibility to save this program. PROLOG will give you possibility to save that. Now we come to the most important topic in this class, and this is the topic of lists. So lists are extremely important because lists are permitting us to process collections of objects. If you have multiple objects that you have to process all of them, this is the most frequent thing that computers are doing. Computers are regularly repeating the same thing many times. And that's what they do as the primary role of computers, is to repeat same computation, calculation, combination, whatever you want, multiple times. So list is an object that permits organization of that by having head and tail. So in PROLOG, list is written in this notation. You have bracket, and then you have components, 1, 2, 3, 4, 5. Whatever, all these objects can be lists, can be whatever complex objects are, but they are separated by commas. Pay attention that in scheme, you have the same thing, but there are no commas. Because in scheme, you have that space is the part of the language. So lists are written 1, 2, 3, 4 with spaces in between. But here, space is not separator. Separator is comma. So 1, 2, 3, 4, 5 has to have this separator comma. Now, how is that stored in memory? In memory, it is stored as a binary tree, terminated by an empty list. So if I have this 1, 2, 3, 4, 5, you have 1, and then here you have subtree 2, subtree 4, 5, and here is terminator that is empty list. So this is the list in PROLOG, in scheme, and in all list-oriented languages. If I don't have here empty list, but have here another number like 6, then this is no longer the list. It is a tree. So you have that each list is a tree. and each tree is not a list. Each list is always a binary tree, but you can have trees that don't have terminator and therefore are not lists. And since they are not lists, they don't have the length because you have to have this terminator to say how many components you have. In graphical notation, you have that this first element here is called the head of list. The rest of them is called the tail of list. So list consists of head followed by tail. Then many of lists are, of course, decomposable into head and tail. And then when you get this tail, you can again decompose tail into head and tail. Then you get this second. And then you have the tail from 3 to 5. And so obviously by chopping heads, chop, 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 you go sequentially through the list and process all elements one after the other. So it is more than clear that this is going to be a mechanism for making loops and process collections of objects in a very elegant way. So many objects are naturally recursive. For example, tree. Tree consists of 2 subtrees. So you take this subtree, and create a tree. Also, recursive objects are very frequently calculations like factorial or maximum or length of list. You can say, what is the length of list? Well, length of list of size n is length of list of size n minus 1 plus 1. Okay. So what is the length of list here? It is length of tail plus 1. That's what is the length of list. And so this is the rule how to compute that. We are going to use that. Basic list operations, there are 5 of them. First, empty list. If you have list that has bracket left and bracket right, and there is nothing inside, that is an empty list. If you have list that has a single component inside, so this is the list with single element, there is nothing more inside. Then you can have this vertical line as the operator that is chopping the head. So when you say head and tail, and you match this with list 1, 2, 3, 4, you are going to have that head is matching 1, and 2, 3, 4 is matching tail. So this is decomposing head and tail of the list. You can decompose head and tail, but you want to use only tail, and then the head is anonymous. So anonymous head and tail is the composition that will use only tail. Or you have the composition of head and tail, where tail is anonymous. That means you only are interested to see what is the first element. What are the other elements? You don't care. They're anonymous. So empty list, list with single element, list with multiple elements that has head and tail, list with anonymous head and tail, and list with head and anonymous tail. You can write that in a variety of ways. You can write 1, 2, 3 list, or you can say I have list, and then after I chop this one, I get 2, 3 as a list here, or I have 2 elements, 1, 2, and then the rest is 3. Pay attention that right of the vertical line must be a list, empty list or whatever. All these notations are equivalent, but we use the first one because it is by far the simplest. So no need to have this vertical line without reason. Now, here is a program that is analyzing a list. So what I want to do is I want to analyze this list 1, 2, 3, 4, and I want to say, is this a list or not? So 1, 2, 3, 4 is a list. Head is 1, and tail is 2, 3, 4. So I want to write this program that is analyzing the list. How to do that? Well, I'm going first to have auxiliary program show list, and then separate, that is separating head and tail, and then we'll show list and separate list in my program analyze. So first show list. I'm going to write the list, so the complete list, and then after that, we'll say either is or is not a list. So there is a library function isList of L that will tell me whether an object is a list. That means this isList is going here through the list from the head to the end and checking whether this data structure has this terminator at the end, or if this is an object in memory that is used by the PROLOG language processor, it is going to have a pointer to this last element, and you will see, is it empty list or not? Is it correct or not? So L is a list. This can be true or false. If it is true, then you say write is. If it is false, you fail here and drop to the next line. Next line is write is not. And then after that, I come and write a list. So I'm going to have, for example, here, 1, 2, 3, vertical line 4. There is no list after vertical line. And my program tells 1, 2, 3, 4 is not a list. Head is 1, tail is 2, 3, 4. So I have to separate head and tail, and I have to write head equals and put right head, new line, tail equals right new light tail, and new line. So as you see, when you say right, this object that is legitimate object of PROLOG language will be displayed. So I have that analyze is show list followed by separate list. So if I analyze 1, 2, 3 vertical line chop, and then you have here list that has 4. So what is this list for? This is a binary tree. It has here 4, and here is empty list. So these are two last elements in the list. Of course, PROLOG tells you 1, 2, 3, 4 is a list, head is 1. You can have also written 1, 2, and then you have sublist 3, 4 that comes after chopping. This is again a list, head is 1, tail is 2, 3, 4. This here is not a list. When you have this in parentheses, this is an object that has 3 or 4, but it is an object that is separated, and therefore it is a binary tree with 3 and 4, and you have that this is a list, head is 1, and tail is having these 2 elements, 2 and 3, 4. But if you have 1, 2, vertical line 3, 4, this is now an error, because you cannot have this data structure. Right of this has to be either a list or has to be an object in parentheses. So you have error message, this 1, 2 vertical, and it says error here. Error is 3, 4. So if I say 1, 2, 1, 2, 3 as a structure of a tree, and 4, everything is okay. It says it is the list. It has head 1, tail 2, 3, 4. How many elements we have here? What is the length of the list? 3 components. And you can have also binary 3, 1, 2. So this is not a list. Head is 1, tail is 2. If you have in this way, you have that head is 1, 2, tail is empty. You can also take the empty list and ask what is head, what is tail. Well, head of an empty list is empty, tail is also empty. Now, this is the last slide for today. We are going to start from here. If you want to show the list, how to show the list? Show the head and then call the same program to show the tail. This is PROLOG recursive thinking. That is called tail recursion. So if you have 100 elements, take the head of this list, display head, and then call the same program to process the tail. And this is the essence of tail recursion as a problem-solving technique. So if you say show list 1, 2, 3, you're going to get 1, 2, 3 elements. So you first show 1, and then you show the list 2, 3. And by doing that, when you come to the end, to empty list, you put new line. So when I say show list 1, 2, 3, I get 1, 2, 3, new line, and then after that, yes, that means it is okay, it is done, but you get the prompt and see what else can be done. Of course, if I show list 1, 2, 3, this is not a list, and you get no, because this is the wrong element. So we'll start from here, try to understand, if you can, this program as a recursive program and see how it works, because it is looping from this show list to this show list, and it is going in this loop and displaying one by one these elements. If you understand how this works, you are going to understand all more complex programs that come later. Any question that I could answer now?